Okay. Now, another problem. Now you will see that once we get the method, okay, we will be able to solve any type of problem. So in the second problem, they told us that a fuel is constituted by 80% in mass, and it's very important to know if the percentage is in mass or volume, because all equations will change. Yani if in case it's volumetric percentages and I need mass percentages, I need to convert them. And we'll discuss this in this example. So we have 80% of in mass of C3H8 propane, and we have 20% of C2H6. And first, we want to calculate the quantity of air required for stoichiometric combustion of fuel. Here there is several approaches to solve such problems. You don't have only one technique, and you are free to use the technique that you feel comfortable with. But one method will suggest the following. We'll say that if I have uh, the percentage in mass of C3H8 and C2H6, if I need to write in one equation the equation of stoichiometric combustion, I need to know the number of kilomoles of C3H8 and C2H6, because if I want to write any equation, let's say I have a kilomole of C3H8 plus b kilomole of C2H6, and I don't know A and B, okay? I can do first the analysis for any value of A and B, and for any number of kilomole of C3H8 plus any number of kilomole of C2H6. And I say that in complete combustion reactions, I need to react this with O2. Okay, and of course, I need to determine what should be the coefficient C of O2 to give me the products of complete combustion. Let's say I have D molecules of CO2 plus E molecules of H2O. So this is the first way of thinking. And I will say, let me find the coefficients D, E, and C function of A and B. And if I calculate what is the number of molecules of A and what is the number of molecules of B, I should be able to determine C, D, E function of them. So I can say first, always the same, whatever is the technique you use, the method is the same. It is the conservation of the mass of elements. The number of C from this side should be equal to the number of C from the other side. Same for H, same for O. By which element we start, always you should say that I start by the elements for which I have them just in one side, in one molecule. If I take, for example, carbon, in the products, carbon is only present in CO2. Okay, so I can automatically say that if I have D molecules of CO2, then the number of kilomole of C is D. Okay, so the number of kilomole of C is D equals to, now each molecules of C3H8 will contain 3 molecules of C. So if I have a kilomole of C3H8, I need to have 3A plus here I have 2B, okay? Because each molecule of C2H6 will contain 2 molecules of C. So knowing A and B, I can determine D. Now I move to element H. So H is present also in the product. It's only present in H2O. So I can say that the number of H, let's say, atoms, okay, is 2 times E. And so, and of course, I can do reasoning by molecule or by kilomole. It's the same concept. So, or if I have, let's say, A kilomole here, I will have here E kilomole. So for the number of kilomole of H, it's 2 times E in the products. So 2E is equal to, here we have A times 8, so 8A plus 6 times B. So this is the equation for H. So again, E is function of A and B. So it's enough to know the number of kilomole of A and number of kilomole of B to determine the coefficients D and E. And finally, for oxygen, oxygen is the most challenging one because in the product it's present in both CO2 and H2O. But now, once I calculate D and E, I can determine the coefficient C here. So I can say that for O, if I consider the number of kilomole of O2 before and after, so after I have for O2 D plus E over 2 because as we mentioned, we need 2 atoms of oxygen to form 1 molecule of O2. So D plus E over 2 is equal to C. Okay. And the question was, what is the number of kilomole of air required? Okay, so we already know that if we know the number of kilomole of oxygen, we can deduce the number of kilomole of air. But here, the main challenge here was to determine A and B. So if we know the percentages in mass of C3H8 and C2H6, how we can deduce in 1 kilogram of fuel what will be the number of kilomole of C3H8 and the number of kilomole of C2H6. All we have to say is to decompose the 1 kilogram. We say in 1 kilogram we have 0.8 kilogram of C3H8 and we have 0.2 kilogram of C2H6. Okay, and now all we have to do is to convert from kilogram to kilomole. Yani we just have to know the molar mass, to find the molar mass, and we know then that in 1 kilogram of fuel we have the number of kilomole of C3H8 is just equal to the number to the mass present, yani it's m over the molar mass. So it's equal to 0.8 kilogram over the molar mass of C3H8. And you know, to get the molar mass, you have to do 3 times the molar mass of carbon, which is 12, plus 8 times 1, because the molar mass of hydrogen is 1. So this is how you can convert. So this will be for UA. This represents the number of kilomole of C3H8 that you have. And to get the number of kilomole of C2H6, you say that B is equal to the mass in 1 kilogram of fuel, which is 0.2, over the molar mass of C2H6, which is 2 times 12 plus 6. So this is a first method, okay? This is a first method, which is to write the general equation and to relate coefficients. So once you get A, B from this analysis, you can replace here to get D, E, and C. And C represents the number of kilomole of O2. You divide by 0.21, you get the number of kilomole of air required for stoichiometric combustion. Now, what is the other method? The other method is the one that we just discussed in the previous problem. And since you already know how to do it, you can profit from using the previous result to answer this problem. From our previous example, we said that the quantity of air in kilomole per kilogram of fuel is just equal to 1 over 0.21 times the percentage in mass of carbon over 12 plus the percentage of mass of hydrogen over 4. So if I want to use this result in my problem here, my only challenge will be to get what is the percentage of carbon in my fuel and what is the percentage in mass of hydrogen in my fuel. And to get them, I should say, first, what do I know? I know that in 1 kilogram of my fuel, I have 0.8 kilogram of C8H, of C3H8, and I have 0.2 kilogram of C2H6. So carbon here has two sources. We have a part coming from C3H8 and a part coming from C2H6. So all we have to do is to determine what is the percentage of mass of carbon in C3H8. So we say that in C3H8, the percentage of in mass of carbon is simply, so C in this component is equal to the mass of carbon in C3H8 over the mass of C3H8. Okay, so we can say the following. If I have one molecule, I can do the reasoning for one molecule. If I have just one molecule of C3H8, the percentage in mass of carbon will be the following. The mass of carbon in this molecule is 3 times 12. And the mass of this molecule is 3 times 12 plus 8. So in this way, I can find what is the percentage of mass of C in C3H8. Okay, so 3 over 12 plus 8. So this percentage of mass represent what? It will give me what is the number of kilogram of C in 1 kilogram of C3H8. And since in my problem, okay, I know that I have 0.8 kilogram of carbon, so of C3H8, I can deduce that in this percentage, okay, the mass of carbon will be just 0.8 times the percentage of in mass of carbon in C3H8. And since we have also another source, so now we should add to this what is the quantity of carbon that is present in 0.2 kilogram of C2H6. So we should add 0.2 times the percentage in carbon in C2H6. Okay. And also it's in a similar way, we can get the percentage of carbon in C2H6 is just 2 times 12 over 2 times 12 plus 6. Okay, so now once you determined these two percentages, all you have to do is to sum the two masses, and then you can get the total mass of carbon present in 1 kilogram of the mixture. So we can say in general, as a general method, so the percentage of C in the mixture, okay, is equal to the summation of the percentage in mass of each element, so sum of Mi, times the percentage of carbon that is present in each of the constituents. So this is how I can determine in total what is the percentage in mass of carbon in the total mixture. And once I do this, I can deduce H, because C plus H is 1, because C is a percentage in mass and H is a percentage in mass. So C plus H is just equal to 1. So once I find the total percentage of C in the mixture, I deduce that H is the percentage in mass of hydrogen is 1 minus C. And then all I have to do is to replace in this equation C and H by their values to get automatically the value of L0. If you use both methods, you will get exactly the same result. So you can use whatever you want, but because at the end the concept is the same. I used conservation of mass before and after the reaction to find my unknowns. Any question on this part?
Yes, Professor, one question. How did we use the equation from problem 1 انه فينا نستعملها وين ما كان هيدي 1 over 0.21.
Okay, هيدي equation in problem 1 شو كان السؤال؟ Find the quantity of oxygen of air in kilomole just required for complete combustion of 1 kilogram of fuel. Okay, so and here, because they are asking you what is the quantity of air.
It's fuel in both exercises. Okay, ما شفت. Okay.
يعني انت in both exercises the fuel is constituted by a certain percentage of carbon and a certain percentage of hydrogen. So since we have same, if you want, constitution of the fuel, and we express this constitution function of the mass, percentage in mass of carbon and percentage in mass of H, so you can use the previous result here.
Yeah, okay.
Okay.
Thanks.
Welcome. So any question on this? Okay, so we were able to answer the first part. Now, in the second part, they are asking us to calculate the change in volume during the combustion process. Okay, if we want to calculate the change in volume, you know that each kilomole will occupy the same volume, whatever is the type of species. Okay, so this is a chemical property. Of course, and I will give you this information in the exam, and no need to memorize this, but you know that each kilomole is occupying 22.4 meter cube. Okay, so to find the change of volume in the process, it's enough to find the change in number of kilomoles. Okay, so if you can determine what is the number of kilomole before combustion and what is the number of kilomole after combustion, the variation between them will tell you if the volume will increase, decrease, or remain the same. So here in this problem, all we have to do is to determine what is the total number of kilomole before and the total number of kilomole after. Okay, so we did already calculation together when we wrote the big equation. If you remember, we said we have A molecules, let's say A kilomole of C3H8, and we have B kilomole of C2H6. So we can just say that we have already A plus B kilomole. Don't forget that we have to add the quantity of air. Okay, we know that the quantity of air just for and here they said we have stoichiometric combustion, so the quantity of air is in kilomole is L0. So the total number of kilomole before the combustion is A plus B plus L0, while since it's a complete combustion, there is only formation of CO2 and H2O. And can you tell me what is also the component that will remain in air as it is? So you know that air is mainly constituted of what? We have 21% of O2, and this O2 will do the combustion completely, and we'll just have the remaining part is N2, and N2 will not do any reactions. So 79% of L0 is from nitrogen, and nitrogen will not react, so it will remain as it is. Okay, that's why we can say that this proportion will remain intact. Okay, so here we'll have at the end also we'll have 0.79 times alpha L0. So this is for the number of kilomole of N2 that will remain here. Okay, and we already found together in the analysis the coefficients. So we calculated the coefficients D and E. Okay, so now all you have to do is to find the change in number of kilomole. So delta N is equal to D plus E plus 0.79 alpha L0 minus the number of kilomole that was already here. So minus A plus B plus L0. Okay, and in case you get a positive result, then the number of kilomole will increase during combustion. So and you can determine the increase in volume by just saying that, you know, each kilomole is occupying 22.4 meter cube. So delta V is equal to delta N times 22.4. Okay, and in case you have a negative result, this means that the volume will decrease during combustion. So this is for the question about the change in volume. Now, in order to calculate the heat of combustion
Doctor,
of the mixture,
one
yes?
question.
Yes.
I'm sorry to interrupt.
Yes, sure.
What is alpha?
Yes,
the
alpha.
incomplete.
Okay.
Yes.
In this problem here, in our problem, what is alpha in this problem? Because of stoichiometric, it's 1. In this problem, it's 1. Okay. But in general, in case the quantity of air, يعني نحن we say the quantity of air in general is alpha times L0. If I tell you in the problem you have a stoichiometric case, this means that you are just giving the required amount of air for combustion, and alpha will be replaced directly by 1. Okay, so here just you have to put 1. Here it's 1 in this problem. Okay. And in case alpha is different than 1, and I can tell you, for example, I am providing extra air, a larger quantity of air than required. In this case, you will consider that you have an additional quantity here. Okay, you have alpha times L0, and at the end of combustion, you will not have only then N2, but if you have extra air, you will have also extra oxygen. And the extra oxygen present will be alpha minus 1 times 0.21 L0, because in the combustion you will have only 21% of L0 that will do combustion, and the remaining part of oxygen will be here. Okay, but in general the quantity of oxygen is not in excess in general, but in case it is in excess, you can just say that at the end of combustion I will have a remaining part of oxygen, which is the initial part minus what was used in the combustion process. Okay?
Okay, thank you.
You're welcome. Okay. Now, in the last part, they asked us for the heat of combustion of the mixture, knowing that for C3H8 is 50.35 megajoule per kilogram, and for C2H6 it is 51.9 megajoule per kilogram. So already in the course material we have seen that for different chemical compositions we have different heat release during combustion. Okay, so in here we know that for C3H8, okay, when we do combustion of 1 kilogram, we get 50.35 megajoule per kilogram. Okay, so 50.35 megajoule per kilogram. Okay, while for the other component, which is C2H6, the heating value is equal to 51.9. Okay, also megajoule per kilogram. Here, please just pay attention to the unit. The unit is very important to know which percentages we should use. Since here we defined the heat in megajoule per kilogram, so we need the percentages in mass to find for 1 kilogram of mixture what will be the heat release. So all I have to say is, if I do the combustion of 1 kilogram of fuel, this 1 kilogram will contain 0.8 kilogram of C3H8, which is, if you want, the percentage in mass of C3H8, which is 80%. And this, if I do the combustion of this 0.8 kilogram, I just have to multiply by the heating value, which is in megajoule per kilogram, to get the amount of heat release. So it's 0.8 times 50.35. Okay, and this should be added, this heating value should be added to the one that is released from the combustion of 0.2 kilogram of C2H6. So I should add 0.2 times 51.9. Okay, now just pay attention. In case, instead of giving you the percentage in mass, they gave you the percentages in volume of C3H8 and C2H6, you should first determine for these percentages of volumes what will be the corresponding percentages of mass, and then calculate the heat value. Okay.
Yes, Professor, can you remind us of the formula to switch from volume to mass?
Okay, look, I don't remember any formula. I will tell you how I will think about it. So for example, if I tell you this, if I tell you that I have, for example, let us consider that the 80% is not for mass. Let us consider the 80% is for volume. And the 20% also is for volume of the second component. You say the following. So in case the percentages were in volume, not in mass, you say, if I have 1 kilomole of mixture this 1 kilomole will contain 0.8 kilomole of C3H8 and will contain 0.2 kilomole of C2H6. Okay, and now you go back to the definition of a percentage in mass. What is the percentage in mass by definition of C3H8? It is simply the mass of C3H8 that is present in this 1 kilomole. Okay, so it's mass of C3H8 in this 1 kilomole divided by the mass of C3H8 plus the mass of C2H6. Okay. And now let us find what is the mass of C3H8 present in this 1 kilomole. If I tell you you have 0.8 kilomole of C3H8, okay, and you know that what is the molar mass of C3H8? We already know that the molar mass is 3 times 12 plus 8. So this is in kilogram per kilomole, okay? In kilogram per kilomole. And since I have only 0.8 kilomole, okay, so I should multiply the molar mass that I have here by 0.8. So I say this is equal to 0.8 times 3 times 12, which is 36 plus 8, over the mass of C3H8, which is I already calculated now, which is 0.8 times 36 plus 8, which is 44. Okay, plus now for the mass of C2H6 that is present in this kilomole, I have 0.2 kilomole, so it's a plus 0.2 times the molar mass of C2H6, so times 2 times 12 plus 6. Okay, so all you have to do is to decompose depending on the percentage that you know, to decompose what you have. If you have the percentage in volume, you say then in 1 kilomole I will have 0.8 kilomole of C3H8 and 0.2 kilomole of C2H6, and then you find what is the corresponding mass of each part. And once you find the mass of each part, you can calculate the percentage in mass of C3H8. And of course, if you do 1 minus this percentage in mass of C3H8, you will get the percentage in mass of C2H6. Okay.
Okay, thanks. Okay, Professor.
Welcome.
طب Professor معقول تحط عمود ال more exercises practice?
Yes, I will. Okay. Other question on this? Okay. Now, concerning the third problem, for the third problem, I just told you if you can just revise the videos of internal combustion engines, because we have already discussed the same cycle, but now we have numbers. In this example, it is easier than we did before. Before, if you remember, we considered the internal combustion cycle of a gasoline engine, which is characterized by a combustion at constant volume process. And we determined together the thermal efficiency of such cycle function of the parameters that we have. So here, if you want, it's an application of this with numbers. Okay, so in problem 3, we have the following. First, they told us that an engine is characterized by an admission of air at a pressure of 0.5 megapascal. So if we start by the admission point here, okay, for this point here, we have the characteristics. We know that here so at this point here, we have a pressure of 0.5 megapascal. And also we know the value of the temperature. So they told us that the temperature here is 330 Kelvin. So this is what we know about the first point here. Now, they also told us that the volume at this point is 0.4 liters. So we have everything, if you want, at this point. At this point, we have all characteristics that are needed. We have pressure, we have temperature, and also we have volume. And you know that because they told us that we can deal with air as ideal gas, so we can use ideal gas formulas. So PV equals MRT. So we can find the mass of the fluid at this point. Okay. Now, the other information given is that pressure elevation ratio during combustion is 1.5. So we know that the combustion process is here. Okay. And if we name points, let's say 1, 2, 3, and 4, they gave us the ratio P3 over P2. So P3 over P2 is equal to the ratio of elevation of pressure, and it's equal here to 1.5. So if we calculate, once we calculate P2, we can deduce the value of P3 by using the following ratio. In addition, also, they told us that the compression ratio is 11. If you remember, the compression ratio is the ratio of the volume at the beginning of the admission to the volume at the end of admission. So it's V1 over V2 is equal to 11. They also told us that we can take air as ideal gas, and we can consider the value of K for air is equal to 1.4. Now, in the first question, they asked us to draw the combustion cycle, and this is what we already did. To remind you of the phases, we have from 1 to 2, we have the admission. Okay, sorry, already here we considered that we admitted the gas, okay, because we are considering the theoretical cycle. So from here we have already the admission done, and we are compressing air inside the cylinder. So 1, 2 is the compression phase. And we know that this compression phase from our previous analysis is a adiabatic process. So the equation of this process is PV to the power K is equal to a constant. Okay. And from the information provided here, since we know the value of V1, we can deduce the value here of V1, we can deduce the value of V2, okay? So V2 is simply, we replace V1 by 0.4, so we can get that V2 is 0.4 over 11. So we know the volume at this point, it's 0.4 liters over 11.